So welcome back, and today we will be seeing what is the current transformer. That is the first classification in instrument transformers. And before going into that, why they are called as instrument transformers? See, these are transformers which are used along with measuring instruments, and that is why they are called as instrument transformers. So, instrument transformers used along with ammeters or current coil of a wattmeter, they are called as current transformers. And instrument transformers which are used along with voltmeters or pressure coils of wattmeters are called potential transformers or simply PT. So these are the two different classifications of transformers. And why they are used, why instrument transformers are used, already we have learned about provisions for extension of ranges of ammeters and voltmeters or wattmeters also. So we can use shunts or series multipliers for extension. So having such a provision, why do we have to go with instrument transformers? See, there are so many difficulties in having shunts and series multipliers. One of the reason is that for AC measurements, since the current carrying coil is stationary, you can measure straight away. You can measure up to 50 amperes. So there is no need for shunts, and the shunts and series multipliers have their own disadvantage. I have discussed. I have given a material so that you can read and understand. So and the thing is that the main thing is that the operating personnel is very close to the measuring instrument, and where the measuring instrument is measuring very high currents or voltages, so that also brings into picture the safety issue. So that is one reason why we are preferring instrument transformers. Okay, so there are some few more reasons, especially the division of current in shunts that is not equal, and that depends on the ratio of R by X in the case of AC circuits, not like DC circuits. So there are so many reasons for that. And we'll start with what is current transformers. So in yesterday's discussion, we have seen this equivalent circuit and the phasor diagram of transformer. Okay, and a current transformer is used with the primary connected in uh, series with the current carrying circuit. Okay, so of course the transmission line will be carrying very high current, so that conductor itself is taken as a primary of the instrument transformer. That current the current carried through the transmission line is taken as the current is taken as the primary current, and the conductor itself, the transmission line or the line where the load is connected, is considered as the primary itself. So a single conductor can be treated as a turn with one turn, that is n is equal to 1. So that is why already I mentioned that when you mention for a transformer step up or step down, you can say that step up and step down are meant for voltages by default, or without any intimation. You can just treat that it is for voltages. Step up means the voltage is being stepped up, step down means the voltage is being stepped down. Okay, so I yesterday told that transformers are rated in kVA, that is power in the primary circuit and power in the secondary circuit will remain the same. That is V1 I1 should be equal to V2 I2. So if I step up the voltage, then current should be stepped down. If I step down the voltage, then current should be stepped up. Then only the equation will be maintained. So a current transformer is actually a step up transformer. That is when you step up the voltage, you step down the current. That is what you require. That is, when you step up the voltage, the current will be stepped down. So here also, when the conductor is having only one turn, or when the conductor is the transmission line, or the conductor when the primary turns is the conductor itself, then you if you have few more turns in the secondary, then that becomes a step up transformer. So step up transformer means in the secondary side you can have a lower value of current. So having a lower value of current, you can easily measure with a usual ammeter or a usual current coil of a wattmeter. There is no need to extend the range further. So a typical value of current transformer is a rating, I'll just tell a rating, that is 100 bar 5 amps. That is a typical rating of a current transformer, 100 bar 5, meaning if primary current is 100 amps, that is equivalent to 5 amps in the secondary, or 5 amps current measured in the secondary is equivalent to 100 amps in the primary. So you cannot measure straight away 100 amps using a conventional ammeter, but you can measure it with an instrument transformer where that 100 amps is converted to 5 amps. So seeing 5 amps in the secondary circuit, you can know that is equivalent to 100, that is equal to 100 amps in the primary circuit. So if you know the transformation ratio, then having measured the value in the secondary circuit, having measured the current value in the secondary circuit, you can easily get the primary current, and that is how the instrument transformer helps in measuring high values of currents. Okay, that is the introduction. So that whatever I told in words is expressed in the figure there. You are having the actual circuit. So that conductor will itself act as a primary winding. Only one or few turns are there, and the secondary winding is having more turns than the primary. And in the secondary circuit, you are having ammeter or both ammeter and a current coil of a wattmeter. So current coil of the wattmeter and ammeter is their ranges are extended by the use of the current transformer there. Okay, so yeah, here few terms are expressed, that is you can just read, that is small n, that is turns ratio, number of secondary winding turns to number of primary winding turns. Rs and Re are the resistance and reactance. Sorry, Rs is resistance of the secondary winding, and Xs is the reactance of the secondary winding. Re resistance of the external burden or the load connected, or the here the for a instrument transformer, the burden is the measuring instrument itself. So the external load is actually the impedance of the measuring instrument. So impedance have two parts, that is resistance and reactance. So resistance of that external burden or the meter, then reactance of the external burden or the meter connected. Then EP and ES are primary winding and secondary winding induced voltages respectively. Then NP and NS, number of turns of primary and secondary winding respectively. VS, voltage across secondary winding terminals. So yesterday also I told that E represents the induced voltages and V represents the terminal voltages. So IS, secondary winding current, IP, primary winding current. Then theta is very important, that is phase angle of the transformer. We'll come to that. Then phi, the working flux of the transformer. Yesterday also we have seen that. Then delta, angle between ES and IS. Then capital delta, that is angle between VS and IS. Okay, so what is small delta? Tan inverse of XS plus XC by RS plus RE. And capital delta is tan inverse of XC by RE. Then as explained earlier in the last lecture, that is I naught is nothing but no load current, and I naught has two components, that is one is magnetizing component IM in phase with phi, and IE is the loss component of exciting current in phase with the supply voltage. Okay, and alpha is the angle between I naught and flux. Okay, so this is the equivalent circuit. So the core can be represented or replaced by a parallel connection of RC and XM. RC represents the primary winding resistance. That is a loss. That is when a part of I naught will be, yesterday also I discussed, the part of I naught will be causing I square R losses in the primary. So RC represents that's the resistance of the core. And then XM represents the reactance of the core. So this XM results in IM. Okay, IM is the current flowing through XM. So IM component actually creates a flux, and IE component actually creates I square R losses in the core. Okay, and then everything is explained. That is I missed one thing, that is if RS and RXS are the resistance and reactance of the secondary circuit, then RP, small rp and small xp will be the resistance and reactance of the primary circuit respectively. I forgot to mark that in figure 1. So VP and VS are the terminal voltage. VP is the supply voltage, that is excitation. VS is the terminal voltage, that is what is the voltage appearing across the burden of the CT or the measuring instrument. And RE and XE are the what yesterday also explained, that is RE and XE are the resistance and reactance of the measuring instrument circuit. Okay, And this is the phasor diagram. Explain yesterday also I have explained in detail. You can just understand. Phi we have explained yesterday. Then I naught has two components, Im and IE. IE is along the supply voltage, and Im is along the flux phi, and angle between I naught and phi already defined, that is angle alpha. And IP, the primary current, has two components. One is the component of the secondary current, that is given by NIS, and the other component is I naught. So you can see that is parallel to I naught. You just draw the phasor, draw a dotted line, and parallel to NIS you draw another dotted line, so that the entire thing becomes a parallelogram. And using the parallelogram method of addition, vector addition, you can find what is IP. Okay. And what is small delta? Small delta is nothing but the angle between, you can just go to the secondary side of the phasor diagram, that is downward in figure 2. So delta, small delta, is the angle between ES and IS. So ES is extended upwards and IS is also extended upwards as NIS. So that becomes the angle, small delta, marked in the quadrant 1 in figure 2. So that is delta, and you can just see the angles there. So theta is nothing but, I told that it's the phase angle of the transformer, that is the angle between IP and IS reversed, that is NIS, that is theta. And delta, as explained, is the angle between the secondary terminal voltage VS and the secondary current IS. And you can just understand from yesterday's discussion how you can draw ISRS, and perpendicular to that you have to draw ISXS, and ISRS will be having the same direction of IS, and everything in total, VS plus ISRS plus J ISXS will give yes. Okay, so I just zoom my attention to the first quadrant, that is in figure 3. You can see the first quadrant of figure 2. Okay, and that is zoomed, and I have just made a construction, temporary construction there. I extend the line OA so that I get a right angle triangle OBC. You can see from that figure, you extend the line OA so that you get a right angle triangle OBC, where angle OBC is 90 degree. Okay, and then what is the angle, what is the angle BOC? Sorry, not BOC, angle BAC. What is the angle BAC? Angle BAC is nothing but, you can just see and understand, that is 90 minus alpha minus delta. 90 minus alpha minus delta. That is, the entire angle is 90 degree. From that, to get that angle, what is that 90 minus alpha minus delta? That is, that dotted line is nothing but equivalent to I naught, and the other thing is equivalent to NIS. So that angle is nothing but the angle between NIS and I naught. So whatever I'm talking about is the angle between NIS and I naught. So what is the total angle? Total angle is 90 degree. From that, to get that angle, you have to minus delta and alpha. That is the angle 90 minus alpha minus delta. Okay, then you have to use the Pythagoras theorem. That is, what is Pythagoras theorem? Hypotenuse square equal to the square of the sum of the two sides, other sides. So OC square equal to OB square plus BC square. And what is OB? OB is the sum of OA and OAB. So instead of OB, you can substitute OA plus AB. So OA plus AB the whole square. And one more thing, what is angle AAB? That is 90 minus delta minus alpha. And you should write the sides in terms of the values of currents. That is, AC is nothing but I naught, OA is nothing but NIS, OC is nothing but IP. So what is BC? BC you can just calculate. If you know the angle 90 minus alpha minus delta, if you take the sine component, you can get BC value. So BC is I naught sine 90 minus delta minus alpha, which is equal to I naught cos delta plus alpha. Similarly, AB is equal to I naught sine delta plus alpha. So substituting everything in the equation, that is OC square is equal to OA plus AB the whole square plus BC square. Instead of OC square, you can substitute as IP square, and instead of OA, you can substitute as NIS. Instead of AB, you can substitute I naught sine delta plus alpha, and instead of BC, you can substitute I naught cos delta plus alpha. Everything is substituted. A plus B the whole square expansion is done. Okay, and you can just understand that I naught square sine square delta plus alpha plus I naught square cos square delta plus alpha is simply I naught square. So that is what is written there. So what is IP? IP is nothing but n square is square plus 2ns is I naught sine delta plus alpha plus I naught square, the whole raised to 1 by 2. Okay, and the transformation ratio is nothing but R is equal to IP by IS. So dividing the whole thing by IS, we get equation number 1. Now, in a well-defined transformer, I naught is very, very small with respect to NIS. So I told that IP is having two components, I naught as well as the component of secondary current, that is NIS. So I naught is only 1% of NIS. So that means the almost whole of IP is nothing but NIS, or IP can be approximately taken equal as NIS. So what I'm talking is that I naught is very small. So for a very small current, if you find the square term, it becomes even smaller. Okay, so to a smaller quantity, if I substitute a term sine square delta plus alpha to a small quantity I naught square, if I substitute a square, or if you multiply even another square term, that is sine square of delta plus alpha, then that doesn't make any change. So why should I make such an approximation? That is a valid approximation because I naught itself is very small and I naught square is even smaller. So to that, if I multiply a square angle, then that doesn't make any change. That is why. So why should I make such a change? See, keeping the equation in the form of 1, equation number 1 doesn't make any sense. You cannot simplify that. You should bring that in the form of a plus b the whole square. So to that, I just substitute, I just multiply I naught square with sine square delta plus alpha. So that becomes what? NIS plus I naught sine delta plus alpha the whole square. So over that there is a 1 by 2, that is everything is coming under root. So that square and that root gets cancelled. What is remaining is R approximately equal to NIS plus I naught sine delta plus alpha divided by IS. So if we divide the whole thing by IS, the remaining things will be N plus I naught divided by IS sine delta plus alpha. From here itself, you can just see that there is a ratio error. This is the actual transformation ratio. That is actually ideally that should be equal to R should be equal to small n. But here you can see that the actual transformation ratio of the transformer is nothing but n with something added to that n. That is I naught plus IS sine delta plus alpha is coming in addition to n. Okay, ideally it should be small n. Okay, and again, if I expand using sine a plus b equation, you can write that as sine delta cos alpha plus cos delta sine alpha. But from the figure itself, you can just see that is IE is equal to I naught sine alpha and IM is equal to I naught cos alpha. Substituting that, you can just write it as N plus IM sine delta plus IE cos delta divided by IS. So that is the transformation ratio R. And I told that phase angle is very important. See, from this figure, you can figure 2, you can just see that is ideally for an instrumentation transformer, that is the secondary current and the primary current should be exactly 180-degree opposite, or that they should be directly opposing each other. That is, for a well-defined current instrument transformer, the secondary current or a current transformer, secondary current should be directly opposing IP. That is, IS and IP should be 180-degree opposite. So in figure you can see that is not the case. Why? If that was the case, then theta should be equal to 0. If that was the case, if IS and IP, if they are 180-degree out of phase, then theta should be equal to 0. So that is not the case here. Theta is not equal to 0. So theta has a small, even though theta is very small, but there is an angle theta. Why? IS and IP are not exactly 180-degree opposite, or they are misplaced by a small angle theta from 180-degree. From being 180-degree, they are displaced by or misplaced by an angle theta. So that angle theta is nothing but the phase angle of the transformer. So that phase angle theta is actually the phase angle error also. Actually, that should not be there. Theta should be equal to 0. Ideally, theta should be equal to 0. So if theta should be equal to 0, they should be out of phase by 180-degree. That is, IS and IP should be misplaced by 180-degree. So that is not the case here. There's a small difference, that is theta, and that is called the phase angle of the transformer, and that itself is called the phase angle error of the transformer. So that is very easy to you just find tan theta. So tan theta is nothing but BC by OB from that figure. BC by OB, you can in the similar lines you can write it as a sum of OA plus AB. Everything you have defined BC, OA and AB in terms of currents. You just substitute that, and I told that theta is even though theta is there, theta is very small, so tan theta is equivalently equal to theta. So if theta is very small, if you find the sine of theta, cos of theta, tan theta, everything will be equivalent to theta itself. So theta is very small, so tan theta is approximately equal to theta. So theta equal to I naught cos delta plus alpha divided by NIS plus I naught sine delta plus alpha. And since I naught is very very smaller than NIS, you can just neglect terms of I naught sine delta plus alpha. So numerator is simply NIS, and you can substitute the expansion of cos A plus B, that is cos delta plus alpha, can be written as I naught cos delta cos alpha minus I naught sine delta sine alpha. Okay, so in the similar lines we can substitute for I naught cos alpha. It is nothing but I naught cos alpha is nothing but Im, and I naught sine alpha is nothing but IE. Substituting that, you get this, you can get the values like that. That is theta approximately equal to Im cos delta minus IE sine delta divided by NIS radians. So if you want to convert that radians into degrees, you have to simply multiply the whole thing by 180 degree by pi. Okay, so ratio error is nothing but nominal ratio minus actual ratio by actual ratio. So nominal ratio is nothing but Kn. Okay, that what is nominal ratio? I already have given the materials. That is rated primary current to rated secondary current. Okay, that is nominal ratio. Actual ratio is what we have found now, that is capital R. So Kn minus capital R divided by capital R. And if you want to express in percentage, you have to multiply it by 100. That is the ratio error. Phase angle theta itself is the phase angle error. So whatever we have found earlier is nothing but the phase angle error. So these are the things which you have to understand in terms of current transformers. There are two errors, that is ratio error as well as phase angle error, and the derivation is very important and very simple to understand also. If you simply know what is Pythagoras theorem, rest is very simple. Okay, so learn that. In examination point of view, this is very important, and till this much you can expect for your first internals. Thank you.